Good morning, everybody. Thank you for coming. Since we are almost there, welcome to the session of Landslides, Friday morning, the champion ones. So now the next speaker will be.
Can you hear me?
Our next
Cool.
speaker
Okay.
is Magdalena Vasileva from GFZ. Floor is yours.
Okay. So good morning, everyone, and thank you for being here with not so much coffee in our blood, early morning on Friday, last day. And I'm going to talk about, satellite remote sensing and landslide. I try to simplify my huge title, but you will see more in detail what is the message I want to give you today. So we know that we have some external forces that can trigger, we have a slope and they can trigger landslides, very simplified figure. And we have two aspects to analyze. We have the aspects of the triggering factors and the aspects of the kinematics of the landslide. And to do this, we need data. Okay, this is just a map of where we can find some landslides. So it's kind of all over the world. This means that it's difficult to get in situ data because we have no idea where the landslide can happen. It happens, we go there, we want to analyze it, and we have no in situ data. So we go to satellites. And this is very kind of classical beginning of a landslide. In spring 2019 in Iran, there was a huge event of rainfall, huge period of rainfalls, which triggered a lot of floods all around the region, all around the country. And they also triggered thousands of landslides. And one of these was in the Hossein-Abad Karpush village. But why we picked this landslide from the thousands of landslides? Because there was something interesting going on. And this is it. In 2013, there was a dam built and a dam reservoir impoundment started. And the landslide happened exactly on the downslope next to the dam. So there's an earth dam. The earth dam was completely stable, but the natural slope next to it failed. And as you can see from the geological map, actually the landslide happened on a relict landslide. And and people, they built a reservoir next to this landslide-prone area. And to analyze this, so we use different remote sensing data. We use optical data to analyze the co-failure. We use SAR data to analyze or to check if there were some precursors and there were some deformations after the failure. And we also use some optical and precipitation meteorological satellite data to extract some information about the possible external factors. And we did some processing to extract time series, to try to correlate them and try to interpret all of this. And these are the data set, all the data I have used for the analysis. So this shows all the insert, the pixel correlation, also the extraction of information about the water reservoir, etc. And there is, unlikely a data gap in my insert time series of between 2010 2014. And I'm skipping also the post-failure analysis because we don't have so much time. And so first of all, I tried to extract some external factors. I used optical planet and Landsat 8 data to extract the high of the water. And I built, if you can see this pinkish color, this is actually the high of my water reservoir change in time. And precipitation, we have a huge long time series of precipitation. We see where we have some anomalies in precipitation, and you can see this peak in 2019 very nicely. And so first of all, I start with the co-failure because, it failed. We wanted to understand how it failed, what was the mechanism. And from the time series of pixel correlation analysis, we saw how it started to fail from the top and kind of the failure propagated to the bottom of the landslide. And it shifted, the maximum shift on the upper part was more than 40 meters. And this mechanism is kind of typical for deep-seated landslide. So then we started to ask ourselves, was this landslide moving previously? And we started with some MVSAT data. Of course, the density in time is very low. It's a lot of errors, probably, a lot of noise. But anyway, when we plot in line of sight the displacement, we don't see a real trend in our results. So we kind of assume that there was no deformation, not very visible deformation before the dam construction, because, okay, the dam, they started to build it in 2019, they completed it in 2013, and from the beginning of 2013, they started to impound the reservoir. So this is the case before the dam or the reservoir presence. And from the precipitation time series, we don't see, or there are some precipitation anomalies, but we don't see change in trends in our displacement maps. And also just checking at the single interferograms, there were no signal about deformation. So we really believe that there was nothing going on before. When we look at the Sentinel-1 data, okay, we're very happy because we have a dense time series. So 2014, 2019 is marked just before the landslide collapse. And we see nicely that when we decompose vertical and horizontal displacement, we see that the horizontal component is predominant and is almost like 30 centimeters of shift in 4.5 years. And but okay, here is kind of starts the story, because it's very difficult to choose what to plot and what to analyze as a time series. So this is was a lot of trying, and the final results that gave better and easy interpretation was the solution to pick a cluster, so to classify or like to segment in space the landslide based on the topography and based on the cumulative horizontal displacement. So we cluster it in 3 different clusters. So this was kind of automatic procedure. And then we extracted the average displacement for these 3 clusters. And what we see is this one here. And for me, it's very interesting because you can see that from the lower sector to the middle to the upper sector, we see that actually the first to destabilize was the lower sector. And already in 2014, when the time series started, there was already kind of a displacement, very small displacement signal, which, okay, when we get velocity in the first year, is like 3.5 centimeters per year. And then after a few months, the middle sector started to destabilize. And after 1.5 years from the beginning, also the upper sector started to destabilize. So this nicely shows, this kind of plotting nicely shows this retrogressive progression of the instability of the landslide. And this was, we were able to show it only by picking the clusters. And when we combine it with our precipitation and water reservoir data, we see that actually these changes in trend correlate very well with the peaks of water reservoir high. So, yeah. And our interpretation was that, okay, we have a kind of a constant force because we have, okay, precipitation are seasonal phenomena, so we expect to have some kind of seasonal changes. And in this case, the water reservoir acts as a permanent force because the water is always there, it's just increasing water level. And that's why it's kind of destabilizing first the lower part, and then as the water goes up, it's starting to destabilize also the middle and upper part. If you go to the vertical component, okay, the vertical component is very small, but when we remove this trend, we get some kind of seasonality. And we did kind of cross-Warland transform using the precipitation data, and we see kind of nice correlation with precipitation. So we see that actually precipitation in this pre-failure stage act only on the shallower layer of the landslide. So it's just swelling and shrinkage of the soil, but it's not acting in the depth of the landslide. And I was talking about this procedure, what to plot and how to extract time series. So we also try PCA, ACA, but as you can see, they're very difficult to interpret because, okay, from PCA you can see just this kind of predominant signal that is kind of increasing in time, but you don't see this retrogressive mechanism that we were seeing by using simple clustering. This is another procedure. I also try to project ascending and descending along the slope, but again, it's like you have 2 different geometries kind of projected. They're kind of different sometimes. It's more difficult to interpret, so that's why it's like it was very difficult. That's why we were trying more easy approach to extract less data, more concentrated, more average together, but that gives much more clear idea of what is going on this landslide. And so this is just a synthesis. You can see that, we nicely can see that a relict landslide started to move because of this water impoundment, and this is just a sketch. I hope you can follow it without my explanation. But yeah, something that I wanted to highlight is that at the end, in the month before the failure, we didn't see in INSAR any kind of increase in velocity. And this is because, sure, the temporal resolution of INSAR. So I again want to highlight that INSAR using Sentinel-1 data it cannot actually be used for early warning because you can't use these precursors that you can have in the weeks or days before the failure. And the second is, okay, the triggers of the 2019 is a bit more complicated to distinguish the different components because in the case of the failure, we had already 4.5 years of slow motion. So for sure, the slope somehow degraded mechanically. So we need to consider this. Then there was the extreme precipitation that for sure they had a major role in the failure. But there was also the water level of the reservoir in that period went above what was the plan of the high level. So it was, let's say, the project wanted to keep it up to 30 meters, and it went 4 meters above this level. So this is kind of added more stress on the slope, and of course. All these factors are very difficult to separate only using INSAR, so this is also another message I wanted to give. But anyway, we were able to kind of understand which are the factors that kind of influence, but then separate the components or kind of the effect of each of them is more difficult, and we need to go through more complex modeling for that. And some very general conclusions, okay. When we analyze landslides, it's true that most of them, they're influenced by a rainfall, but we need to consider also the anthropogenic factors, which can be, in this case, okay, it was water reservoir, but also we should consider the land use change, which is also a big factor for that can influence the stability of landslide. And we can, this very in-depth analysis of landslides shows how using multi-sensor and multi-variable satellite data, we can nicely not only have information about the kinematics, but also about more about the triggering factors and the mechanism of the landslide itself. So go into more interpretation instead of, okay, the landslide is moving or is accelerating. So really understand why it's accelerating, why it's moving. And this time series extraction strategies. So it's kind of, I think there is no common way of extracting time series and analyzing. I saw papers, okay, people using just picking points or picking small areas or clustering or doing PCA, whatever. So also this is kind of interesting to, I don't know, understand which is the best strategy to pick this time series, because at the end you are basing your analysis on those time series that you're extracting. So this is just a few photos from our fieldwork in Iran, and thank you.
Okay, thank you very much. Nice presentation. We have time for questions. Okay, maybe we can start. Do you think, because you started with a global map
Yes.
of landslide, how generalized do you think your approach could fit globally analyzing 10 landslides?
Okay, I don't think it's, okay. So there's no a global approach. This is the problem. And I wanted to show that this landslide was kind of a different based compared to other landslides that are more, okay, I start again, sorry. So most of the landslides, they happen because of rainfall, and therefore all the approaches that have been developed, they're very rainfall oriented. So in my case, I show that actually also anthropogenic factors can influence. So we need to, when considered globally, we need to consider much more factors and not only rainfall. So this is the message I wanted to give.
Thank you.
Oh,
Hello, thank you for your presentation. Did you had any monitoring on the dam that you could compare your satellite data with?
you mean for the water reservoir?
Yes.
Yes, actually, this was the starting point. I was supposed to use those data, and I had no permission to publish them. So at the end, I had the data, but because of that, I needed to find a new way to extract the data. So I extract them, and then secretly I compared them.
Okay, but do they have like any alarm in their system?
No, they don't. It's just very easygoing dam that, yeah. Now they're, okay, after this failure, they reduced the height of the water and they're keeping it in between lower levels, let's say. And actually, okay, I'm not showing here the post failure deformations, but it's stabilizing now because they're also taking other measurements for stabilizing the slope. Yeah.
Okay, thank you.
Thank you very much. Okay.
Yes.
Just a quick one.
Just a question about the method you use to extract the water level 8 from the optical data. Which data did you use?
Yes, sorry.
Which way you extract?
Yeah, of course. So I try to find all the available optical data in the period from 2013 until now, and I found Landsat 8 from April 2013, and then PlanetScope because we had access to those data, and it's much better because it's 3-meter resolution. So I use those data, and then I use SRTM, which shows anyway the topography before the dam construction. So this helped a lot. And I use a QGIS approach. I simply choose a profile quite next or as close as possible to my slope, but that had kind of more gentle slope, so I could separate more easily the changes. And I kind of pick where the water extent and then merge it with this profile and topography. So that this is how I built my time series. Does it answer?
Yeah, thanks.
Okay.
Okay, very nice. We change the next speaker. Thank you very much. Now, John Dells from the Geological Survey of Norway will show us how to explore potential ISA imagery operation landslide monitoring. The floor is yours.
Thank you very much. We had a very good presentation earlier this week from Urs Wegmüller about various experiments with ISI, and I want to follow up with a bit more focus on the use of it for operational monitoring. So just a little bit of background. So I'm with the Geological Survey of Norway, and together with NORSE, we have built a national ground motion service, the Norwegian Ground Motion Service. We launched it 2018, and we're processing about 4,000 scenes a year with annual updates to the data set. So in this process, in this service, we download all available Sentinel-1 scenes covering Norway every single night automatically. And as we download them, they are automatically unzipped and co-registered to existing stacks of data, a lot of pre-processing done. And then just once a year, we do the final step of the PSI analysis to extract the deformation. So we have a dedicated computing cluster where we do all this work. And the results we put out in our Explorer interface, it's a fully 3-dimensional map where you can go zoom it around and see about 5 billion measurement points. And if it looks familiar to you, it's because this is the same platform that we use for the European Ground Motion Service. So in Norway, at the survey, we've been using INSAR data for, well, more than 20 years now. And using a lot for mapping of potential rock slope failures. So we initially worked with ERS data and RadarSat-2 data years ago when we first got coverage with RadarSat-2 over very large areas. The plot on the lower left here is showing the cumulative number of unstable slopes we've identified over the years. And you can see that when we started taking into account RadarSat-2 data, we were able to find a lot of sites. But as RadarSat-2 data was commercial, we had a limited quota. We couldn't cover the entire country. With the first data set that we launched with Sentinel-1 in 2018, this is the first time we had full nationwide coverage. And within months, we had discovered over 100 new unstable rock slopes, which led to a lot of fieldwork the next year. This is just one example of such a block. This is approximately 50 million cubic meters of rock that's unstable up in very northernmost Norway. In this case, there's no particular hazard right below the landslide, but right about 10 kilometers across the fjord is a small settlement which would be destroyed if this rock failure occurred and caused a tsunami. So as we're systematically mapping the country now, we've identified more than 1,000 unstable slopes, or potentially unstable slopes, which we've been working on. And as we identify them, we have a systematic procedure to do a hazard and risk classification. And our aim with this is to, as quickly as possible, find the ones that aren't a problem and not concentrate on them, and concentrate on the ones that are potentially higher risk. So in this hazard and risk classification, we take into account a lot of different parameters about the geometry of the sites and other rock slope movements and things like this. But velocity is very important, so we use INSAR for that, not just for identifying the landslides, but also to understand their motion. So currently in Norway, we have identified 10 or 11 sites as being high risk, where there are threatening populations. And in each of these sites, we have abundant in situ instrumentation in place. We also have a number of sites where we're monitoring over time to identify them, whether or not they're a threat or not. So in these sites, we also do periodic monitoring. And of course, having snow for half of the year in Norway, roughly, we need to use corner reflectors in order to get a data series throughout the year. And this has become something that we do a lot in Norway. So currently we have more than 25 locations where we've installed corner reflector networks. And these are mounted on masts about 2 meters high to make sure they stay above the snow. They are covered to prevent snow accumulation. And we use either single geometry or dual geometry corner reflectors, depending on the location and coverage from the satellites. Oops, next. Okay, so corner reflectors are very, very useful for us. They're not always easy to get into place. Of course, it's challenging logistics to put them in place. And this is one of the samples I'll show later in more detail in northern Norway. And here we need to use helicopters to move everything in place. But once these corner reflector networks are in place and installed, of course, they require no maintenance and no data transmission or anything else. So they're very, very practical. So during our nightly operations for INSAR Norway, as we're downloading all these stacks and pre-processing and everything, we automatically throughout the night then also process each of these corner reflector networks every single night. And these data are automatically transferred over to the Norwegian Water and Energy Authority, who's doing the day-to-day monitoring of these sites and going into the systems along with all the other data from in situ instrumentation. And they're able to access this from their monitoring center and so on. So going back to the same example, which I showed the installation from, this is a site where we've installed the corner reflectors back in 2012 to use with RadarSat-2 data. You can see with RadarSat-2, we had, of course, new measurements every 24 days. There are gaps in the time series because being a commercial satellite, sometimes there were conflicts, commercial conflicts in accessing the satellite, or perhaps, of course, there might have been failures once in a while. With the advent of Sentinel-1, we suddenly had a vastly improved access to data. Not just because the acquisition plan of Sentinel-1 is very reliable and gives you the data every 12 days as you expect it, but also because being at a higher latitude, you see this is the typical 6 to 12-day acquisition pattern over Norway. You have a lot of overlap between adjacent tracks, so we get a number of geometries. So in this particular case, we have 6 different tracks, or 3 different tracks that cover the area. in descending, and therefore we're getting, when we had Sentinel-1A and B operating, we had data measurements almost every day. Every 1 to 2 days, we were able to sample with one or the other of these. Unfortunately, we now have lost Sentinel-1B. So that has reduced the frequency of data sets by half, obviously, but more importantly for us, it's taken away any redundancy we had in the system, because in many of these sites, we are relying on these corner reflectors to provide the information that allows us to declare that people can live in this area, for example. So we needed to do something about redundancy. So we started looking into commercial data to supplement the Sentinel-1 until we have 1C back up in the orbit. At the same time, we had an opportunity we discussed with ISI the possibility of experimenting with their data. So we chose the same region for this test site because we have 4 unstable slopes there, which are highly instrumented. So it's a very great test site to test any methods. We've been using it for many years with different systems. So anyway, in the summer of 2022, we collected 58 strip map mode images between June 22nd and September 29th. So altogether about 99 days of coverage. You can see the baseline plot there. So there were some gaps due to commercial reasons, also because there were some small gaps due to orbital maneuvers and a large gap due to commercial reasons. Nonetheless, it was very useful. So just zooming in again on the location, as I mentioned, there's 4 unstable rock slopes there, where we have corner reflector networks installed. There's the ISI image to the right. So what were the main challenges with ISI? One thing, of course, was the orbital characteristics. Here's the baseline plot with a reference to seen in early September. And you can see it's a huge range of baselines compared to, for example, what we're used to with other satellites. So this is, more than 15 kilometers in range. And the other issue we had was the quality of the orbital information that we received from about these scenes. So these very long baselines required the use of a DEM in order to do the co-registration. And also because these baselines are very correlated between the temporal and spatial baseline, we needed to use the full cycle in order to get a proper processing, because we can't really calculate the DEM error very well otherwise. Oops, I think this is out of sequence, but that doesn't really matter. This is the average intensity image for one part of the image, showing the results after co-registration, which I'll get back to in a minute. And if we zoom in a little bit closer here, you can see very clearly the corner reflectors on these slopes shining brightly, along with some points along the road due to infrastructure. And also in Indre Norden, as you see up at the highest part, just below where the text is labeled, there's a set of corner reflectors. So getting back to the methodology. So as I mentioned, there was also inside from the actual characteristics of the baseline, there was also fairly large errors, more than 10 meters in the annotated orbits that we received. So this meant that we needed to do not our standard techniques for co-registration. Luckily, of course, we had these 20 corner reflectors within the area of interest, and so we were able to do, first of all, an initial correction of the reference scene using the corner reflector locations, which we knew to within centimeters. And then we also did a first order orbit correction on all the rest of the stacks using these corner reflectors. Then we used a sort of a standard classical patch correlation methods to reduce, to do the final orbit correction, and did geometric co-registration using DEM. So getting on to the results. Okay, so here's a one-day interferogram from this area, and you can see there are no phase ramps within the image, so we know that the orbit correction was done correctly. Most of this, of course, is atmosphere, but if you look closely, and I'll get back to it on my final example, there's actually some motion shown in this single-day interferogram as well. So here's the first site, which we call Yetan, which has a set of 9 corner reflectors, or rather 1 reference and 8 other corner reflectors installed. Here we see the overall time series of Sentinel-1 data with the ISI put in 2022 and with the zoomed in. And you can see that the ISI data matched very well, of course, with the Sentinel-1 data as expected and a very similar quality of measurements. Moving into another site called Revdalsfjell. It's a little easier to see the time series here because there's fewer of them. Here we see quite a linear plus seasonal motion over the years. The ISI data, if you just looked at the ISI data, you would say that was quite a large scatter and it's quite noisy data. But you can see that it's actually the same level of noise as we have with Sentinel-1. It's just that such a short time series with such frequent sampling that it appears noisy. But in fact, the quality is just as good as Sentinel-1. This is the first example that I showed again, going back to Gammon Uni. Here we have a number of in situ things that we can measure with, but I'll just concentrate on the corner reflectors with satellite. Just picking out, we have done some previous analysis here of the time series. The top plot shows the overall time series, which is mostly linear, but there's also a seasonal component in there of a few millimeters per year. If we zoom in closer, again, we see how well the ISI fits within these time series. Just to note, the reason why these Sentinel time series are slightly separated in the plot is simply because they have slightly different acquisition geometries, and this is line of sight. So they diverge over time. Another example, the final example of corner reflectors, this is a site called Indernornes. Now, this is a site that's been quite a concern for us the last few years because it has quite a significant seasonal acceleration every year. And as you can see from the plot on the right, this is the Sentinel-1 data, that there's been this summer acceleration every year has been increasing and increasing. So 2022 was quite high. So you see here again the ISI data plotted in there. Unfortunately, we hadn't started acquiring before the acceleration in the spring, so that would have been very interesting to see. But nonetheless, once again, we see how well it matches, but of course with a much higher temporal sampling. And just as a note, this is just the Sentinel-1 data going forward into this year, and this year's seasonal acceleration was less than the previous year. So we're a little bit relieved, but we're still very closely monitoring this site. The orange dots there are Cosmo SkyMet data because we're supplementing here with Cosmo in order to maintain the redundancy. One final case example. This is a series of a set of rock glaciers up in the same region, which we've been studying before. This rock glacier complex is moving quite rapidly, more than 10 meters per year.
1 minute.
And this 10 meters per year, of course, is much too high for us normally to be able to measure using Sentinel-1. The bottom image shows a clip from our INSAR ground motion service using Sentinel-1, and you can see that most of the slope, well, you see some areas that are moving, most of it is devoid of points. However, if we look at the ISI, this is a zoom in on the same one-day interferogram that I showed earlier, and you can quite clearly see that in a number of these sites, we see actually multiple fringes within a single day of deformation. And on the left-hand side, this is a simple stacking of all the 1 and 2 day interferograms. And here you can see that color scale is plus or minus 2 meters per year. So you can see of course, the advantage of everyday orbit or sampling of the time series. So just to conclude, this ISI, what they call daily coherent ground track repeat product, provided us nearly daily corner reflector measurements with very similar quality to Sentinel-1. So that was very positive. And these large drifting baselines were not a problem at all for us to do corner reflector processing. However, for any sort of operational PSI, DSI type or SPAS processing, of course, the baselines would preferably be much, much smaller, less than 1 kilometer or 500 meters preferred. Also, the orbital information really, really needs to be better. The only way we were able to successfully do the necessary co-registration as well as we did here is because we already had these corner reflectors that we could use in order to do the initial correction. Also, of course, as I mentioned in the last example, the daily repeat coverage allows us to resolve very fast motion, which we couldn't before. currently there's very limited availability of this product, yeah, so in the future, we hope that with more missions and more satellites, that this will be more obtainable for most people. Thank you.
Thank you very much, John. Time for questions. Yep, is there one?
Thank you very much for very good results, actually. I have two questions. First question, how do you deal with the topographic phase removal? Also, what kind of DM you use for the co-registration, because you mentioned it's important. And second question, how do you deal with the topographic atmospheric effect in such a big differences in the topography? Thank you.
For the first question, we use the 10-meter resolution DEM, which is available for Norway. So that's good enough in this case. We don't need to do anything more higher resolution. For our corner reflector processing, of course, we have no way to correct for atmospheres, but we design our corner reflector networks taking that into account. So we try to keep the vertical, for example, the reference point, the vertical difference between the reference points and the moving reflectors as tight as possible, you know, within limits, but it's not really an issue for that. If we were using this using standard PSI and DSI, then we would use standard atmospheric corrections methods.
More questions? I think, okay, you good?
Hi, thank you for the presentation. So you said you put corner reflectors on the snowy area, right? So how do you keep the snow from the corner reflectors?
Yeah, they have a plexiglass cover. So they're standard trihedral corner reflector, but we have a plexiglass cover over it. So mostly the snow just slides off. Occasionally during the winter, we do see some, if it's been very icy kind of weather, we can see some drop in signal but usually it's not an issue.
Thank you.
And also they're 2 meters high, so they stay up, they don't get covered in snow.
Mm-hmm.
Okay,
You have a question? No.
okay, thank you. Thank you very much.
Thank you very much.
Okay, we can move to the next presentation given by Katie Allen Burrows from FRINGE. Yeah, the talk will be an application of Sentinel-1 amplitude and coherence time series to rapid landslides triggering during long rainfall events. The floor is yours.
Okay. Thank you. The coherence part of this talk will actually not exist, so I'm sorry if anyone's come for that. Yes, I will be looking at how we can use Sentinel-1 amplitude to time rapid landslides during long rainfall events. So when we want to characterize the mass wasting, so the volume of landslide material, and the hazard that's posed by rainfall-triggered landslides, we need to get information on their spatial extent and on their timing. And with satellite images, we can map landslides at a large spatial scale. So gathering information on the spatial extent of landslides is quite easy. So for example, here we have a pre-monsoon and post-monsoon image of Nepal in 2017. And by comparing the two, you can see new failures in the second image. And then you just draw polygons around them. And then you have a map of their spatial extent. And this process is very boring and it takes a very long time to do, but we're getting quite good at automating it and it does work quite well. You can then use these to make susceptibility maps and things like this, and to direct or decide about whether you're going to build infrastructure in certain places and things like this. However, the problem is that between these two images, in this example, in the monsoon, pretty much all the images are filled with clouds, so we can't use them to work out when during the monsoon the landslide happened. And this is also a problem if you have successive typhoons or sequences of earthquakes. It's especially a problem with rainfall-triggered landslides because clouds are what causes the rain. So you can almost never get a good timing in tropical areas. So the solution we've come up with for this is to map the landslides first in optical satellite images, and then to have a second step where you use Sentinel-1 time series to constrain their timings. And we developed a method of doing this that's actually based on 4 sub-techniques that we use together. So the first one is to take the difference through time between the pixels within the landslide polygon and similar pixels that lie within a buffer region around the outside of the landslide. The second is increased variability between landslide pixels. So in general, we expect that, or we found that before the landslide happens, your imaging, Sentinel-1 is just imaging the canopy, and that's fairly uniform, but after the landslide happens, you have a scar, and it maybe has big boulders and bits of trees in it, and it has forest still growing around the outside, so it's a lot more variable than it was before. And we then have 2 more methods that are based on the 3D shape of the landslide in comparison to the diagonal viewing angle of the sensor. So in general, we expect to have shadows cast by trees on the edge of the landslide. And then on the other side, we sometimes get this double bounce mechanism, which in vertically polarized SAR leads to bright spots on the side of the landslide polygon. So for each landslide polygon, we can get 4 time series, and we're expecting each one to have a permanent change in it, because on the timescale we're looking at, the landslide is permanent. It's not going to have revegetated by the end of the year. So to get this step change, we convolve with a step function, so it's quite a basic way of getting it. And in this case, in this one landslide, all 4 techniques have given the same result. So we assessed all the techniques, and we found that individually they're not reliable enough, but if you have at least 2 of the techniques giving you the same date, then you can assume that this date is probably correct. It's correct 80% of the time. And at least 30% of the landslides in an inventory can be timed using this. So because I usually explain this quite badly, so I've put a pie chart in. But in the pie chart, the green ones are ones that we can't time at all. The red ones are timed correctly, and the orange ones are timed incorrectly. And there's more information on this in the paper we published in NHES in 2022. And the method is very helpful when you have landslides triggered by sequences of storms and earthquakes. And the other place it's helpful is in the Nepal monsoon. So now I'm going to talk about some of the things we can do with landslide timing. So in Nepal, heavy rainfall triggers thousands of landslides every year. And this image is from a paper where they mapped landslides every year for 30 years. So it's a huge data set, but this was done using optical satellite images. And using this data, you can get susceptibility maps, but you can't tell when the landslides happen. So that's what we decided to do. And the importance of doing this is highlighted by another figure from their paper. So in this, each point represents 1 year's worth of landslides. And they found that the volume on the y-axis is in most cases proportional to the total rainfall during the monsoon. And that's because the main triggering factor is the progressive accumulation of soil water during the monsoon. So in general, at the beginning of the monsoon, the soil is completely dry and it rains for months and months, and gradually at some point you have so much water built up in the soil that it becomes unstable and fails. But they also found that in 2 years, so the 2 blue points on the graph, there were cloudbursts, and these years had anomalously high levels of landslides. And also in 2015, the monsoon season immediately followed a magnitude 7.8 earthquake. And we also have anomalously high landslides in 2015 and possibly in 2016. So altogether, we have 3 different triggering factors that are influencing landslides in Nepal every monsoon. If we want to begin to untangle this complicated thing, we can use the landslide timing information. So here, this is a map of all the landslides we managed to time over 4 years. So 2015, 17, 18, and 19. There were a lot of Sentinel-1 images missing in 2016, so we skipped that year. And on the left, there is a histogram showing the timings of the landslides. And you can see from this that the overall timing varies a lot between years. So for example, in 2017, we have a huge peak and this corresponds to a particular storm that happened in August. Then you can see in 2018, most of the landslides happened towards the end of the monsoon. And this reflects more what I was saying about how the soil water gradually builds up. So landslides are more likely at the end than at the beginning. And finally, you can see that in 2015, the year after the earthquake, we have a lot of very early landslides that occur very soon after the monsoon starts. So first, I'm going to look at how these intense storms can impact landslides. So with the timing information, we're able to identify spatio-temporal clusters of landslides. And then by looking at news reports and satellite rainfall products and rain gauges, we can associate the clusters of landslides with specific periods of intense rainfall. So in the top map in 2017, this was the biggest spatio-temporal cluster we found. And this year, actually, 40% of the landslides were triggered by a 3-day heavy rainfall event that happened in the south of the country. So that means, that kind of indicates that that essentially just that storms can have a very big impact on landslides. And this is important because in Nepal, it's sort of expected that due to climate change, the total amount of rainfall might decrease, but the number of storms is probably going to increase. So if we want to understand how the hazard's going to evolve in the coming years, we need to begin to balance these two effects. And the 2018 map demonstrates the importance of having the timing information. Because so with the spatial data, we found a cluster in this top left-hand corner. But once we looked at it using the timing information as well, we found it's actually not, it's one spatial cluster, but it's actually made up of 2 spatio-temporal clusters where half of them were triggered by an intense rainfall event on the 13th of September, and the others are more likely to have been triggered. It's thought that they were triggered by snowfall because there is no recorded intense rainfall event in mid-August, but that's what we've timed them all by. So clearly intense storms are important in Nepal for landslide triggering, and we'll try and study this more in the future. So now I'll move on to looking at how the earthquake impacted the landslide timings. And I will do that by, what we did was we modeled the amount of soil water that was, the amount of water that was in the soil at the time when every landslide failed in our inventory. And we did this using a really basic model called the leaky bucket model, where essentially you have rain going in, which we got from the GPM satellite, and evaporation coming out, which is known based on other studies. I think they measure it from the vegetation. And at some point, as the monsoon progresses, the bucket fills up. And at some point, you reach this hole in the bucket, which is the fill capacity of the system, and you begin to have drainage. And in general, it's not expected that you should have many landslides happening before you hit this field capacity. And you can see that in 2017 to 19, that is the case. Most of the landslides plot above this line. But in 2015, we have a lot of landslides happening in pretty dry conditions, which is not what you would expect in a normal year. So whether a landslide fails or not is controlled by the soil water content, the slope steepness, and the internal friction and cohesion of the soil, which together just represent how strong the hill slope is. So if we have landslides failing in drier conditions on the same slopes, then we need to have a weaker internal friction and cohesion to explain this. And by putting this all into, this thing at the top is described by an equation called the factor of safety equation, which I didn't put in the interest of not having equations because it's too early in the morning for that. But you can invert the equation to work out how much weaker you need your hill slopes to be to explain how much drier your landslides are. And we found that we got a cohesion drop of between 1 and 4,000 pascals. And this is quite cool because it's it's a new application of Sentinel-1. It's a new way to look at post-seismic weakening after earthquakes. So we should be able to do this in other locations as well. And because you can do it with satellite data, you will begin to get a footprint of how wide your post-seismic weakening effect is. But unfortunately, in this case, all our landslides were included in this zone, so we didn't actually reach the edge. But if we expanded our study area, we might be able to map the post-seismic weakening footprint, which would be quite cool. So in conclusion, we've made a method so that Sentinel-1 amplitude can be used to assign 12-day windows to 30% of landslides in an inventory with 80% accuracy. Hopefully, we'll be able to get both of these percentages up a bit by refining the method, and also once we have L-band satellites acquiring on regular intervals like NISAR and ROSE-L, we know that these work probably a bit better at detecting landslides in vegetated areas, so that should help this work better. And with this timing information, we can better assign landslides to individual storms and earthquakes. And as well as that, in Nepal, we've been able to start untangling the combined effects of the multiple triggers at work there, so the earthquakes, the progressive increases in soil moisture, and individual storms. And this has revealed that in some years, intense localized rainfall accounts for a significant proportion of triggered landslides, so 40% in 2017 is pretty high. And also, it's enabled us to observe earlier and drier landsliding following the 2015 earthquake, and we've been able to explain this by a temporary loss of hill slope strength. So Sentinel-1 has offered us a new way to explore this process. Thank you. That's the end of the talk.
Thank you very much. Very interesting. Any questions from you? There's one question there in the middle.
Thank you. This interesting result. Did you? I'm curious. Did you try to correlate the cohesion with the soil type or rock type?
With what? Sorry.
You have the cohesion plots, right? Did you try to correlate the correlation between the cohesion and the soil type? Different soil type have different cohesion, right?
Oh, the soil type. No, we didn't. Essentially because the survey is on such a wide area that it's not really possible to get good information on the soil. But it would be interesting to do it. But I think you would probably have to gather data from a historical list of field campaigns and stuff. But yes, it would be interesting.
Could you please pass the microphone there?
Thank you very much, Katie. That was a very interesting talk. And my question is, did you see any evidence, or maybe yes or no, that these increase in landslides, or the predominance of landslides, could also be correlated with deforestation on a mass level in this area?
We actually removed. So I went through the landslides that we'd timed in high resolution optical imagery, and removed any that looked like they were actually either touching deforestation or touching areas where they'd built new roads, because we know this can influence the landslide timing, and we wanted to have landslides that were predominantly triggered by rainfall in the analysis only.
Yeah.
Thank you, Kitty. It's excellent work. Actually, I wonder, is there any difference between different land cover type? For example, in your case, you mentioned that there seems it performs good in the forest. Is it perform? Did you check it has any improvement or deterioration in grass or other kinds of land cover?
So we found that the method works a lot better in forested areas. So that's the coherence part of the talk that I thought I would have done by now and haven't, is aiming to try and get it to work a bit better in areas that are less forested. because it should be more sensitive in unforested areas. But I haven't finished this part yet.
Do you think it performs better in non-forest regions?
The amplitude methods we have at the moment perform best in heavily forested areas. Yeah.
And also, is there any landslides that reoccur? For example, they occur again and again. Is it possible to detect such landslides?
So we found that the method at the moment will only detect the first failure. So we're trying to adapt it so that it will detect multi-stage failure at the moment.
Thank you.
Yeah.
Thank you very much again.
Okay, thank you.
Thank you.
Okay, thank you. Now we change to the next speaker, Dylan Christian Hickson from MDA. He's going to talk about slow failure predictions. It'll be quite interesting. Thank you. The floor is yours.
Hey, thank you. Hey, good morning, everyone. Congratulations for making it to the last talk, the full conference. So, yeah, as kind of stated, this talk is looking at ways in which we can constrain slope failure predictions from INSAR analyses. Being the last talk, I kind of had the luxury of getting to reflect on some of the discussions that have happened during the week. And I think this topic has kind of come up in one way or another. There was a discussion at a round table earlier in the week, I think in the displacements and deformations. There's some posters that were discussing this topic and really trying to answer the question of, we have these INSAR deformation measurements. Can we reliably try and extract some kind of alarm or early warning system that would be useful? And so, yeah, this talk is an attempt to try and find a way that we can do that. All right, so I think in this session, I don't need to go much into the significant risk to why we care about these types of landslides. And so in this context, I'm describing both natural landslides. So that's, well, I don't know. I don't know how the laser pointer works here. This one? This, which is an example of a landslide that took place in China. And this example in the bottom left here, which is a tailing storage facility dam collapse. So this is in a mining context. So this is essentially an artificial dam that's built around the mining waste, and it's intended to retain that material. So we're monitoring these sites already for INSAR deformation. And now we want to know, is there a way that we can try and extract some kind of meaningful interpretation of potential failure from that INSAR deformation? And we can leverage extensive research that's been accumulated theoretically and empirically from laboratory measurements on how this pre-failure deformation then relates to the time of failure. So the technique that's typically used to do this is inverse velocity. There's a couple of other ways to do kind of the same thing. So some of you might be familiar with this approach, but it follows the creep theory of deformation, which is basically long-term deformation under a constant stress. And so this creep theory, under this creep theory, strain deforms in three main phases. So there's the primary phase, where you have actually a deceleration of the strain. And then the secondary phase, which can be quite long, depending on the type of failure, which you have this linear accumulation of strain. And then, importantly for landslides and ground failures, the tertiary creep phase, which is characterized by accelerating deformation. And so there's been a lot of empirical models and laboratory experiments that have looked at how this tertiary creep phase progresses and how deformation measurements can kind of track this progression up to the time of failure. And so the inverse velocity technique is fairly simple. If you have accelerating deformation, and you take the integral of that, that relates to a constant velocity, so a constant deformation rate. And then if you plot the inverse of that deformation rate, you get inverse velocity. And so this is the typical equation that's used for this. In most applications, especially with satellite INSAR, the linear model is assumed for simplicity. And so you track kind of measurements through this tertiary creep phase up to some measurement point where you have your last measurement. You try and extrapolate that to the time axis, and where this model intercepts the time axis gives you a predicted life expectancy. So for anyone familiar with this technique, this is just a basic overview, but this is the method in which we're trying to relate INSAR deformation measurements to time of failure predictions. So something I wanted to touch on is a distinction that needs to be made between applying this in a ground-based setting versus satellite INSAR. So there's been some work that's looked at how phase ambiguities from satellite INSAR and temporal sampling, so our limitations with repeat cycles, how that can impact this analysis. And I wanted to illustrate this in a very simple example using simulations and a Monte Carlo simulation. So here on the top is a simple accelerating deformation profile where I've approximated a ground-based instrumentation with daily sampling and a satellite INSAR scenario with 12-day repeats, so Sentinel-1 scenario. And then converting that into deformation rate in the middle plot, then plotting the inverse of that rate, so the inverse velocity, and then applying this inverse velocity model fitting. And so you can see for this one instance, we get a roughly linear trend from both the ground-based and satellite INSAR data sets, so that's not really surprising. But when we repeat this process 10,000 times and we look at the distribution and these predicted life expectancies for this, this simulation, we see that the ground-based estimates give actually a very tight prediction. And this is where ground-based inverse velocity modeling has found a lot of success, especially in mining application. You have a very consistent stream of very high sampling rate data. And so you can apply different techniques like smoothing, and you have more flexibility in the signal processing that you apply to get better estimates of the failures. Whereas in the satellite INSAR scenario, we're much more sensitive to these very small fluctuations in noise. And so that actually results in a much greater spread of our predicted life expectancies. Interestingly here, you can see that actually kind of the mode of that distribution roughly correlates well with the ground-based instrumentation. So we are extracting some meaningful information, but we have very, very noisy estimates from any single realization of this. And so really with this, I just want to highlight that we have to think about doing this application much differently in the context of satellite INSAR deformation monitoring. And critically, I also wanted to point out that the correlation coefficient of these linear model fits can actually be very good for satellite INSAR. So you can very confidently be not very accurate in your failure prediction. And so in ground-based instrumentation, this is often taken as a proxy for the quality of your failure prediction, which in that instance, if you have your instrumentation ideally oriented for the geometry of the expected failure, given all your site context knowledge, maybe that's the case. But for satellite INSAR, we can't just take this number and kind of use that as our approximation for how good our estimates are. Right, so based on all this, I'm breaking down the approach that we've developed for this in terms of challenges to this problem and then our solution. So the first challenge is we are providing this INSAR deformation monitoring over a wide area where we don't have any knowledge of where potential failure might happen. And we wanted to generalize this as much as possible. So we need a way to focus on where in our INSAR deformation measurements are there signals that we need to follow up on for this kind of modeling. And so as opposed to taking a simple deformation rate threshold or deformation acceleration threshold that might trigger some alarm to follow up on processing, as these might be site dependent, they can depend on the local geology, lots of different factors that we can't reliably tune to every single scenario that we want to apply this. We instead look at changes in deformation trends. And so we run a change point analysis on all of our deformation points. And then we automatically try to identify those that are exhibiting a significant change in the trend that might be related to this onset of acceleration, which is related to that beginning of that tertiary creep phase where you have the accelerating deformation. So once we have this depiction of where we have all of these change points through our deformation time series, we now need to isolate distinct failure zones. So we need to separate these spatially. And so the way we do this is we run an automated spatial and temporal clustering on these measurements that we've identified having this recent change point. And so in this way, we're clustering measurements both spatially but also temporally in that they must be exhibiting similar change points in their deformation time series. And then last, as illustrated in some of these previous slides, our predicted life expectancy estimates will suffer from inherent noise. So that's the noise that's present in our INSAR deformation time series, but also just the result of our sampling frequency in these model fits. And so to overcome this, we compile some statistics on PLE estimates based on these clusters of measurements that are showing consistent trends. And then based on that, we can try and assign some level of confidence in our predicted life expectancies. So just a very high level overview of this algorithm, which kind of summary of what I just described. So we start off with our deformation time series. So we take our most recent deformation image. We then run a change point detection algorithm to identify any onsets of acceleration on a point-by-point basis through that image. We then perform spatial clustering of those points that are exhibiting similar change points. So that's the temporal aspect to our clustering. We then perform this inverse velocity model fitting for each point in each cluster, and then we analyze all of them independently. So this is a prospective analysis in which we are updating our solution as we can, proceed through ongoing monitoring. And so if we identify some type of trend, as we acquire new images, we can perform the same analysis and identify, has that changed our trend estimate, since we can identify deformation trends based on a sequence of measurements. So we can kind of continually update these analyses. We've developed an automatic quality control step in this process, since we might identify many clusters over a region, so that we can automatically try and exclude clusters that are obviously not showing signs that exhibit this type of inverse velocity failure prediction. And then we would follow up with an analyst looking at each cluster that doesn't really get flagged by this process. So the algorithm we developed is vectorized and scalable, so you can apply it over very small areas or over very large areas. And we try to minimize the amount of parameters that have to be tuned, so that this is something that we're just trying to apply on wide scales that's site agnostic, with the aim of really trying to just pull out if any of these signatures exist in our INSAR measurements without making any assumptions about the implications of those model results. So this algorithm can be integrated into an ongoing deformation monitoring program. So every time we acquire a new SAR acquisition, we then update our INSAR stack in our deformation measurements. We rerun this change point detection, apply our clustering and model fitting on those identified clusters, and then report any new changes or update any failure predictions that might be consistent from one acquisition to the next. So this consistency allows us to look back at previous acquisitions and compare how a failure prediction might have changed. Maybe it goes away, maybe it gets more confident, but we have that kind of history of these predictions that we can use to inform the analysis. So as I mentioned, it's site agnostic. It's applicable over wide areas. We perform the statistical analysis of the PLEs so that we can try and quantify our confidence in the failure prediction. And then we incorporate our results into our online data visualization platform so that our deformation monitoring is kind of accompanied by this result. So to try and benchmark the accuracy of our method, we applied it in 3 case studies where there's a ground failure from creep deformation that occurred in a region where we have INSAR compatible SAR imagery. So I've anonymized the 3 sites that we applied it to here. If you're familiar with these studies, you might be able to just recognize them from the images. So here I have the date of the failure, the type of structure. So 2 open pit mining scenarios, and 1 was a tailing storage facility. And for all 3 of these analyses, we've used RadarSat-2 data. So in each case, we created a cumulative deformation product up to the last acquisition available preceding the collapse. For these, we've actually looked back, like repeating this analysis for kind of the second last acquisition, the third last acquisition, and trying to see how our analyses change through that. So just for purposes of time, that's not included in today, but that's something that we have looked into. And then once we have that cumulative deformation product, we apply the inverse velocity algorithm that we developed to derive a predicted life expectancy, and then compare that to the true time of failure for these 3 cases. So here's the first site that we looked at. This is the tailing storage facility that exhibited an embankment fail on March 9th of 2018. So in the before image, you can see the section of the tailing storage facility that failed before it failed. And then on the bottom, you can see the section that ended up failing. For this, we use Spotlight RadarSat-2 data. So very high resolution, a relatively small stack size because we want to try and perform these analyses in the context of an ongoing deformation program, where we're not keeping track of extremely long time series, but we're trying to kind of keep this analysis in a window that's relevant to what is the most recent data that we have. And so you can see here in this cumulative vertical deformation image that we measured significant deformation all along the tailing storage facility embankment, but specifically in the region that was around the collapse. And then this is the result of our inverse velocity algorithm. So on the top left, I'm showing individual deformation profile for one pixel that I selected just randomly in that failure zone. And so you can pretty clearly see visually where the accelerating deformation starts, and our change point detection algorithm identifies that automatically. Then on the image on the right in that map, we're seeing all of the pixels that were clustered that are exhibiting a very similar change trend that are spatially consistent. And then on the bottom left, this is our inverse velocity model fit for this cluster of pixels, in which we've averaged all of our inverse velocity measurements, done a weighted fit to this, which allows us to compute confidence intervals over a regression, which we can then use to constrain our confidence in the predicted life expectancy. And so in this case, you can see this was computed at a 70% confidence level. And so at that level, we have roughly almost 40 days that span our predicted life expectancy prediction. So even though we did actually get a result that's fairly close to the true time of failure, we have this quantification of at the 70% confidence level, we have about, I guess it's 37 days. And then on the right, we've applied a symbology so that you can see these failure predictions on a point-by-point basis in terms of the number of days from the last acquisition. And so anything that's kind of a darker red color is showing something that's more of an imminent failure. Anything that's kind of a paler color is something that could have been a negative predicted life expectancy, so a prediction for a failure that would have already happened. That would be non-physical, or something that's very far in the future. And so you can see that these do show some more of the imminent failure predictions right in the region that we would expect, but it also highlights that we have a lot of scatter in these results. So really the utility of this approach is being able to identify consistent trends, having enough measurements to build up a statistical sample from which you can drive a meaningful estimate. So the second site we applied this to is an open pit mining collapse. And so this is on one of the pit walls. So you can see in the top right, the before image, and in the bottom right, the after image. So it's kind of hard to see, but this section of the wall that failed. And you can see in our cumulative INSAR deformation map that we identified some significant deformation over that region. So this was collected in wide ultrafine strip map mode. And this was a similar stack size, 16 acquisitions, leading right up to the last acquisition we have preceding the failure on November 17th in 2020. So here I'm showing the results very similarly to the first case study. So we see our time series in the top left, a very obvious change point that would be very easy to identify visually that our algorithm's able to pick out as well. This time series is exhibiting some more noise. And in this case, we could be seeing some deceleration in the deformation time series or just a noise fluctuation in our ongoing monitoring. And so actually these very subtle changes in the time series towards the end where we do our inverse velocity fitting really have a huge impact on that final result, which is kind of another illustration of why we need to look at larger samples with this. So then the bottom left is showing our inverse velocity model fitting, similar to the first site. And then on the right, we're seeing the pixel-wise results. And I didn't explain it for the first case study that I showed, but we compute this convex hull around all of our points that are included in this cluster. And so this is roughly the broad region that that our averaged predictions apply to. And then for more focused but noisier estimates, we can look at the point-by-point measurements. And then the last site that I'm showing here is another open pit failure. So this is a very large open pit mine, and you can see there's a very small wall failure that occurred on May 31st, 2021. So for this site, we're using ultra-fine strip map observations, a fairly large stack size, up to the last acquisition preceding the failure. So this is more of a PSI analysis. And so we can see that there's really two kind of sections of the image there showing some really strong deformation. So we have this cluster here that's kind of difficult to see with the coloring, and then this area up here. So in this case, the deformation profile looked remarkably linear. And so we're having difficulty identifying an onset of acceleration. But we also wanted to be able to see if there's a way that we could just apply this analysis to check just in areas that have very strong deformation, is there some possible signal that can be identified? So in this case, we kind of adapt our clustering approach so that we're not looking for these deformation trends. Now we're just looking for very strong deformation. So this isn't as robust as our kind of typical approach. And so in this case, we unsurprisingly identify this as a very strong deformation cluster for which we apply this inverse velocity model fitting. And so we arrive at a result that's fairly consistent with the true time of failure. And this is again shown at the 70% confidence interval, confidence level. And so you can see a fairly large spread in our predictions that are made here. So just to kind of summarize everything, failure forecasting that's done using satellite INSAR observations requires a different approach than what is used for ground-based instrumentation. And I think more importantly, it requires a different approach to interpreting those observations. In the last few examples, you've seen that these failure predictions kind of span several weeks, whereas from a ground-based monitoring perspective, you might have failure predictions that are within hours to a few days, depending on how those are made. And so kind of taking that same thinking and applying it to the satellite INSAR case just isn't a good approach. So we've developed a statistical approach to provide this type of analysis with our deformation monitoring. And we've tried to automate this approach and minimize parameter tuning. We've presented 3 case studies where this analysis was applied in a prospective perspective to forecast impending failures at these known sites. And this approach can be easily incorporated into an ongoing INSAR deformation monitoring program. And so really the main idea is we're trying to focus our analysis in on areas where it's best suited. So starting from a wide area INSAR deformation monitoring, trying to isolate this very strong or accelerating deformation, performing our inverse velocity model fits, and then interpreting those results with some degree of confidence. All right, so that concludes my presentation. So thank you for your attendance.
Okay, thank you very much. Do you have any questions? Well, I have one. Do you have any numbers for false alarms that the method can provide in the? I mean, you are adding days, so maybe you have a failure, and then you add the second one, and it's not failing yet, or?
Yeah, that's a really good point. I think that's one of the major concerns with trying to do this type of approach. So in this case, and I think as is typical with doing this, you end up with a lot of false alarms. So it's how do you interpret those? And so developing this approach in which we can provide a confidence interval that tries to give some context to how to interpret those false alarms. So typically we're sensitive to these kind of longer scale failures over time. So typically we have the opportunity to follow up with more acquisitions once we've identified a trend. So in this case, we can kind of characterize a false positive by how the failure prediction evolves as we acquire new data and how the confidence in that failure prediction changes. And so this is something where we're trying to take kind of a step back and just see what can we statistically pull out of the data provide this to, users who need the information that they can then plug into their other data sets, their own geotechnical expertise for their site, so they can take the confidence metric that we've provided and then interpret that in the context of their other observations. So we haven't really done a thorough analysis of comparing a number of false positives, because in this case, we're trying to not really worry so much about that, but weight how we would interpret those false positives instead.
Thank you. Any other question? No? Thank you very much. Thank you very much, everybody, for the session. Now we're trying to move maybe to the roundtable discussion. So. We prepared some SIP questions, but I will even invite you more to provide recommendations to each other. This is now the last session to be able to collect them for the session summary. As I said, don't feel suggested to buy the question, but you can also express your concerns, your recommendations, and so on. Or we want to maybe discuss something on the questions above, or any other one. I mean, so.
I mean, maybe we can start with the first one that you prepared, Jose.
Yeah, we can.
In which cases shall optical data be used to complement landslides analysis? Shall that kind of analysis be proposed also to EGMS next contract? So yeah, the question is always with the optical data about the clouds, right? And in the connection with the landslides triggers.
Mm-hmm.
So then we can be very, very careful on the quality of this optical data.
Sure. No, but in the past we also see, in some cases, also the image correlation with Sentinel-2 was able to provide information for large movements where INSAR was not enough.
Mm.
So,
Yes.
For the first question, maybe, I don't know, we integrate coherence, time series approach as well.
Mm-hmm.
I mean, it could be feasible. I think the EGMS product itself has a coherence. So we could use like a coherence map time series as an extra layer to add in the EGMS. I mean, it could provide a similar time series analysis that provide the NDVI for the optical. Yeah, could be maybe beneficial to analyze both of them at the same time interval. One could maybe build some statistical, based on the statistics, some interpretation on big landslide activity. So also moving quicker than the normal ones that we are used to analyze with PSI. Yeah.
Okay.
Just as a recommendation.
Yeah.
There's
Some reply. Thank you.
Yeah, I would support the use of coherence change. It's very exciting to see what they have planned for NISAR with the Opera products, because they are planning on having sequences of both radio terrain corrected intensity images plus coherence, and so that should be able to do a very good time series over time. So that would be very useful here in Europe. Whether it's part of EGMS I doubt it, but it would be certainly very complementary to EGMS.
Regarding optical data, it's not always the case, because in many cases there are not visible damages on the optical images. However, on the other sessions, they were proposed another layer, EGMS layer, like soil moisture. I think this is will be very interesting to explore that, and I think that this landslide community could strongly support for having that data.
Yeah, I think that one of the products of the Copernicus land is also the soil moisture. I think it's 1 kilometer grid, something like this. Obviously, a finer resolution will be probably desired as well. Yeah, thanks. I was wondering also as well, would also the EGMS wondering to include also NISAR observations to complement those? That will be also a nice question, but I don't know what the Commission or EA would say about it. And do you know if there are any plans, any suggestions in that regard, Jon? Can you please send it up? Thank you.
I don't think the budget would stretch that far at this point. It would be very exciting if they had the budget to do that.
Thank you. Okay. So then maybe we can go to the second point, which is the potential of exploring new space satellite data for systematic monitoring over landslide areas. Indeed, in your presentation, John, I had a hidden question I could not ask you before. Were you using all ISI data over the area in opportunistic baselines, because you shown a very large one, or only one of the satellites was possibly used for that?
It was one particular. It was the X7 satellite that was configured for
X7.
that. Yeah.
Okay.
So yeah, of course, new space. The main thing with systematic monitoring and mapping of what the revolution with Sentinel-1 was suddenly having global coverage, and with a very boring acquisition plan that gives us reliable data. And the obvious downside with new space is simply, the cost and availability. So if you can afford it, it's great. But
Will be a recommendation for ESA or large space agencies also to produce a small constellation of small satellites with more revisit time, or that will maybe overlap with commercial interest? That's something to be taken into account as well. But will be desired by the community to have also not only Sentinel-1, but large constellation of smaller satellites also, with open free policy at least, will be also interesting.
I'd be happy to just have Sentinel-1 E and F up there at the same time as well. So yeah.
Thank you. Yeah,
on the topic of mission design, I know there were a couple brought up yesterday that discussed co-flyers around Roselle or NISAR that would allow for three-dimensional deformation resolution. I think that's something in particular that would be very valuable for the landslide community, because if landslides have lateral motion predominantly in the north-south direction, we often miss those. It'd be great to give a recommendation to ESA that, the ability to resolve 3D deformation would be in particular very useful to the landslide INSAR community.
I think there was some Capella presentation, they have some satellite in, not low orbit, sorry, not what was that? Not polar orbit, but just medium orbit, in which they were also sensitive to north-south information.
So I just want to add on to what Forrest has recommended. I think because of the uniqueness of the NISAR is not only L-band, but also left-looking. So you have left-looking, descending, ascending, from right-looking, descending, ascending from Sentinel-1. That will give you a lot of information about three-dimensional information mapping, in addition to the densified temporal sampling.
Yeah, I think we're looking forward to the next FRINGE with NISA results. Yeah, it will be amazing. Okay. The third point there in the slides is the shortlist low failure prediction maps be produced operationally, which are the main dependencies. Is INSAR enough? Single or multi-sensor or anything else? So maybe you want to add something there? I think from Dylan said that it was a bit complex still, the prediction. Yeah, so I think it's not yet for operationals, just maybe use case by use case. So if the last one maybe, is Sentinel-1 enough to map fast or very fast landslide events? Which other SAR or not SAR sensors could complement Sentinel-1 operationally?
Well, because I have the microphone, I can say no, of course, right? We are looking at about the fast-moving landslide in Alaska called Barrier Arm landslide. It's funny though, INSAR is of course the one because of the coherence. So we also have little bit snow and then the C-band lost coherence. So I mean, we want to have more NISAR or P-band data would be potentially very useful to look at fast-moving landslide. And so I think that's...
Yeah, thank you. There. Yeah, okay.
Yes, of course, the answer is no. A great data set is L-band, and now we have SAOCOM in space. There are opportunities to get the data in Europe through ASI, which made a very nice work to try to mirror the catalog. Outside Europe, it will be through ESA. The procedure is quite complicated to get the data. You have to order to get to. So my recommendation here is to ESA is to try to push to make the distribution of SAOCOM data easily. And maybe also to push SAOCOM to acquire more and more data, to use the satellites and just get images and distribute them.
Yep.
I don't know if this is feasible, but I think we can put it as a recommendation of the community.
Thank you. No, it's a very good one. I will also add free policy for ALOS 2. That would be also a very nice one. Indeed, I mean, L-band is something that we need to wait for NISAR, at least to have it open and free. The current ones, as you said, is over Europe. I think it was also a really nice plan of acquisitions.
Yes, and the interprograms are very nice, yes.
Yeah.
And we start to do multi-temporal analysis, which is also useful.
Yeah. But indeed, still the way to get the data is not too fast. So yeah, that would be really nice to shorten the procedures, indeed. I don't know what ESA can push for that, I don't know. I know that ESA had, or still has, open call for getting SAOCOM outside the restricted area of Europe. So if any of you want to explore that, I think it's still, as an open call, I think it will end either this month or next month. But yeah, it's a bit complex. The catalog is not too helping so much to see where the data is there. But yeah, I mean, I invite you to give a try. Especially you have somebody from Argentina. They have really nice coverage, and it's easier to get those data over there. But we need to still to deal with all policies of data and hidden catalogs and so on. I hope that will evolve in the future for any of the satellites. That would be a dream. Yes. Okay, so if you have any other questions or any other recommendations that you may have in mind, don't be shy. I think time is now. don't. I think we all want a coffee break now. Well, I can only thank you for all for your participation, and I hope to see you again in the next Fringe, or even before. Thank you very much.
Thank you.
Okay. No, it's fine.